in an experiment.
And we don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, women's health, the menopause and chronic funding disparities.
And a star caught in the act of eating a planet. I'm Nick Petrichow.
And I'm Shamini Bundell. First up, earlier this week, reporter Noah Baker sat down with two of our colleagues from the news team to chat about two feature articles in this week's Nature, both covering different aspects of women's health research. Here's Noah.
Hello, I'm Noah Baker, and I'm joined today by two of Nature's finest to talk about two features all about women's health. Now, we'll get to what we mean exactly by women's health in a moment, but first let me introduce my guests. We have senior reporter Heidi Ledford.
Hello.
And we have features editor Kerry Smith.
Hi, Noah. Thanks for having us.
Two features this week. You've each written one of them. Kerry, I believe you've also edited one of them. And both of them centre around women's health. One about menopause and one about funding. So I think before we get going on this, we should just clarify that when we say women's health here, this is an imperfect catch-all term that we're using. For example, not all people who identify as women will go through the menopause, but there are also transgender men and non-binary folks or intersex folks that could be affected by other of the health conditions that we're going to discuss. So it's an imperfect term. Scientific studies also define women and women's health in various different ways, but for the sake of this conversation, this is the term we're going to be using. And I think we should probably kick off with Heidi, your feature on the menopause. So to start with, this is menopause and the brain. Where did this sort of brainchild of an idea come from?
I think it came from Kerry coming to me at some point and saying, hey, we should do some sort of feature about menopause. It's a fairly broad mandate. But then in the course of looking through some of the grant proposals, so some of the grants that had been awarded through the U.S. National Institutes of Health, I remember reading through the abstracts of them and thinking, oh, this is really a brain thing, isn't it? I mean, it seems really obvious, oh, wow, look, the sky is blue, isn't it? But I just had thought of it so much as being a reproductive organ thing.
Yeah, and people might be aware of symptoms like brain fog that people discuss, anxiety
Absolutely.
symptoms, sleep disruption.
Yeah.
These are all things that can be related to the brain, right?
Exactly.
You started digging into the research that's out there. What is the focus?
What we decided to focus on was this transition period leading into menopause. So menopause technically is defined as the state that you reach after you've gone for a year with no menstruation, right? But there's this long period before that where hormone levels start to vary in unusual ways. The body, it's sort of like laying the groundwork, I guess, for menopause, but in a kind of weird and unpredictable way. So, a woman becomes sort of accustomed to this cycle of hormones, up and down. And the brain becomes accustomed to that cycle of hormones going up and down. And that affects, the brain's metabolism. But then you hit perimenopause and suddenly that cycle becomes disrupted and the hormones are going up and down in unusual ways, sometimes more muted, sometimes more exaggerated changes. And it kind of throws some of the brain's metabolism and so forth into disarray before it has a chance to get used to life without as much estrogen around, for example.
So in terms of what research can be done, this first research that you talk about in your feature was from 1990. That seems drastically late for an early piece of research in a feature.
Yeah, I mean, there are lots of reasons why the research there has lagged. And some of it, I think Kerry will get into funding for women's health research writ large and how, that maybe has lagged compared to some other fields. The other thing, too, though, is that it's hard to study. I mean, it's, animal models aren't great for menopause. Menopause is not something, it doesn't occur in mice and rats, for example, in the same way that it does in humans. And so it's difficult then to model. It's also hard to study because it varies so much from woman to woman. So some women will sail through perimenopause, menopause, barely noticing anything, right? And other women will have very severe symptoms that can last for a decade or more. So it just makes it really challenging even to study from an epidemiological standpoint, if so many people are having so many different kinds of experiences. We did open this story talking about one researcher in particular named Naomi Rantz, who had decided, she happened to come from the sort of background that it kind of led her to this field, I guess, and she was studying sort of post-mortem brains, I guess, and looking at the differences that she could see in postmenopausal brains versus premenopausal brains. And she noticed some neurons that looked a bit bigger after menopause. And then she noticed that they seemed to respond to a particular signaling molecule in the brain called neurokinin B. And eventually that's now leading to a class of drugs that are coming out to treat hot flashes. It's such a hallmark, of menopause.
Yeah, and one that's tied to the brain, to the hypothalamus, right? That's something that people are
That's
aware
right. It's
of.
tied to the hypothalamus. And I spoke to one researcher about that, and she said, she wants to study hot flashes in menopause, but she realized that there's so little known actually about the perception of body temperature and body temperature regulation in the hypothalamus that she's having to step back further and further away from the question that she wanted to get at, just so that she could get the foundation laid for that.
One thing that was very clear whilst reading your feature is that there is an awful lot that's still unknown, which, I would like to say I'm very surprised about, again, given the significance and the prevalence of perimenopause and menopause within people. But unfortunately, 10 years in this job has left me unsurprised by that. And that's something that, Kerry, you've been looking into a lot as well, about funding more broadly. You actually have an entire feature discussing funding for women's health. Was it a surprise to you when you saw that come across your desk when Heidi wrote that copy?
Well, I think one of the things that prompted us to include this piece on women's health funding was the fact that we had discovered through Heidi's feature that menopause funding is actually very hard to track, at least in the US, where the NIH, the National Institutes of Health, is very good actually at publishing data and cataloging data on what they fund, and they're the world's biggest funder of biomedical research. They actually don't track what they spend on menopause. It's very hard to find that information out. And I guess I got thinking, well, what if that's the case with other conditions, not necessarily even ones that are specific to the female physiology, if you like, or to women, but disorders that affect the sexes differently. And so that's what I ended up looking at in this second feature, is what's the kind of landscape of research funding.
I found this feature really fascinating to look through, and also these charts really fascinating to interrogate. And part of the reason for that is you've used some measures which are maybe not what I would expect or what you classically see.
Yeah, I guess I should say first that part of these are our choices, but actually we're completely led by what research is available and what researchers have, what analyses researchers have done of these conditions, and only certain metrics are made available, and some of them are the favorites of health economists. One of the classics is the DALY, in fact, so I'll start with that, which is a measure of both the death and the disability that a certain disease causes, and it allows you to compare on a little more even grounding, maybe a cancer that's fatal a lot of the time, to a condition like endometriosis, for example, which we wouldn't necessarily associate with a lot of deaths, but we would associate with a high kind of burden to the people who have it and to the population. And then the other metric, the QALY or the QALY, is a kind of quality adjusted life year. This is what it stands for. The DALY is the disability adjusted life year. What it represents is the kind of economic cost of a year of perfect health.
And this is particularly relevant here if you're talking about conditions like endometriosis, for example, or even menopause, that are not necessarily killing people, but have a really, really significant effect on people's lives. What were you broadly seeing when you started to look at these data and put them into charts that people can see on the website?
So a lot of the graphics that we put together were based on data that from a 2021 paper, and the author of that paper provided us with up-to-date information. He looked at NIH data, and what this analysis looked at was whether there was a relationship between how much funding a disease gets and how much burden it gets, and then whether that differs for conditions that are women dominant or men dominant. And surprise, surprise, the analysis found that there was a relationship, and that diseases that were female dominant were more often underfunded, and sometimes by a sort of greater degree.
And was this analysis showing novel things? Was this a representation of things that were broadly understood within the clinical field, or are there things that were surprises that came up as a result of doing this analysis in this way?
I think, well, the surprising thing to me is that actually it hadn't been done by anybody in a very official capacity. So this guy was actually a retired academic. He's an applied mathematician. He used to put together highly complex climate models, and his daughter was diagnosed with ME/CFS, and he decided to look at whether there was a stream of funding to this and how it compared with the burden, and found that disease gets very little funding compared to its burden. And then he broadened out and looked at these other conditions. But I mean, nobody paid him for that. He's not affiliated with a university. He's not got a decades of experience studying health funding or women's health. Not to be derogatory of his analysis, which has been cited in a lot of places and is considered robust, but just to highlight that, you know, this is not a large field of research by any means. So I suppose that was a surprise to me. Less of a surprise, unfortunately, as we've kind of said, is the message.
Yeah, and this is about the burden with relation to funding, but you also looked at things like clinical trials, and the same kind of disparities arose there as well.
Yeah, we present some data in the piece that has to do with whether women are represented in clinical trials in proportion to the frequency with which they get certain disorders. So there's actually long been a kind of assumption that women are underrepresented across the board in clinical trials. And that historically was the case. In fact, due to the thalidomide tragedy where babies were born with congenital defects because their mothers were given a drug, there was a widespread sort of nervousness about enlisting women in clinical trials after that. So today's data sort of suggests that the bias overall is not quite as prevalent. So according to NIH data, again, about half of participants in clinical trials are women. But there is a discrepancy, and there was a large analysis that looked at 20,000 clinical trials. There are some discrepancies if you look at certain subject matters. So in oncology, in cancer, and in neurology. But in fact, in other fields, they're overrepresented. So the picture has, I think, gotten a little more complex.
Yeah, it's very interesting, this in terms of just trying to be representative in your clinical trial cohorts. It feels like perhaps these trials could just be a bit more tailored to the populations they're trying to help in the first place.
Yeah, I think that's a really important point. And I mean, I should stress that we only really looked here at men and women, and we haven't even begun, or maybe we should, an analysis of how science, how research, how funding, how clinical trials deal with more of an intersectional picture.
But one thing you did do as well in this feature is you did something which, often in this sort of feature I don't get to see, which is show the impact of making a change. And that was really quite drastic. Can you take us through that?
Yes, I can certainly try. It's a little more hypothetical, I suppose, because it's a modelling study put together by two non-profit organisations. And they put together these studies for a few conditions that are more likely to affect women. For example, rheumatoid arthritis, coronary artery disease, and Alzheimer's disease. And they looked at whether an increase, a sort of conservative sort of doubling of the current women's health budget, and I think when they did this study, that was kind of 2019 or 2020. If you doubled that, would you see an increase in the next 30 years of, healthy life? And would you see economic impacts as well? And so that's why we, at the very beginning, were talking about Quailies, because that was one of the analyses that if you topped up women-specific funding for rheumatoid arthritis, they assumed you get, a small bump in health improvement, and that would have huge impacts on the quality of life and people's productivity. They'd be able to return to work more, and that would reduce the costs of the disease by over $10 billion over this 30-year period, which equates to a ridiculous return on investment, basically. You can look at the real number. It's got six figures in the piece, but that was pretty staggering.
Yeah, and you said, they assumed a small bump in health improvement as a result of the increased funding. And it really is a small bump. It's 0.1% health improvement. It's a very reasonable assumption with really incredibly large return on investment. And that just really speaks to the amount of people that are affected by these conditions in the first place and how expensive it is to manage that.
Yeah, I mean, reasonable is one word. They would certainly say conservative. I think they erred on the side of caution with each of the assumptions that they put into the model, how much return on investment, how much health improvement, and that sort of thing. And they've still got these really big numbers. And as a result, there's actually a bill moving through Congress right now, put forward by two Congress people, that is asking to double the investment in women's health. So that's been one concrete kind of outcome of these reports.
And if we were to sort of put our broad thinking hats on and try to get to the bottom of why these disparities exist. Now, I don't believe we can get to the bottom of why all these disparities exist in this one podcast, because there's a lot of very complex reasons. But often things are cited that are kind of very relevant to what Heidi was talking about as well. Like, for example, hot flashes are not seen as a priority because they're not lethal. But that doesn't mean that they don't have a really drastic impact on people's lives when you're trying to face
Yeah,
them.
I mean, I think when you start talking about women's health, you get into all sorts of issues. I think Carrie talked about, the thalidomide example and that, being one of the reasons why women were excluded from clinical trials for a reason that was, intended to be protective, right, of newborn children and so forth. you can also think back to when so many animal studies were done only using male animals. Well, why was that? Well, in part because the female animals had these hormonal cycles and they just didn't want that noise in the data, right? So it's sort of, you have these sort of old reasons that feed into these disparities. But you also, certainly when you talk to women, you hear lots of stories about their health concerns being dismissed, right? It's a fairly common refrain I've heard a lot. I could even say I've experienced at times, right? A friend and I were talking the other day about menopause and about how we were talking about how younger women now are so much more willing to talk about reproductive issues, about their periods, about menopause, about things like that. God, I love them for it. I love it because when I was brought up, you didn't really talk about some of these things. They were taboo, right? We have this idea that it could be used against us, right? Like in the workplace, if we have this disability that makes us less of a good worker, then maybe we don't get promoted. Maybe we don't get the job. Maybe we whatever, So for her, it still feels very uncomfortable to talk about a lot of these things because, all of this kind of feeds into this sort of dysfunctional ecosystem where maybe for some good reasons we're overlooked in clinical trials, maybe for some discriminatory reasons we're not being included in clinical trials, maybe for some just social economic reasons we're not being included in clinical trials, but then that ends up resulting in, these exacerbating disparities and so forth. It's a very complicated situation.
And there is an example in your feature of, an advert talking about a drug specifically that we talked about earlier for menopause being shown during the Super Bowl. And that blew the minds of the researchers you were talking about because it's so unusual, right, to have that be so public in its discourse.
I had such mixed feelings about that, though, Because on the one hand, oh, wow, look, we're talking about it. And at the Super Bowl of all places, right, to talk about what some women go through when they go through perimenopause. But on the other hand, I thought, oh, here comes pharma. And, we want there to be treatments for people, but also at least in the, when you live in the United States and there's such a sort of medical capitalism kind of ethos there that I hope it goes well.
Indeed. And, I'm sitting in New York right now, and we are also in a context which adds more complication to the mix where, a large part of the discussion within the United States politically is about access to reproductive healthcare. And certainly in certain states, that's really under threat right now, which certainly impacts any discussion we could have about equality, fairness, access to healthcare, specifically access to women's health and reproductive health.
I guess it points also to the importance of data, and keeping an eye on what changes as a result of these policy changes in the different states. What we have data on what that's going to lead to for women, but to document it as it happens and to make sure that people realize what kind of impact these policies have.
Heidi, Kerry, thank you so much for joining me. It's been fascinating to talk through these topics. There's loads and loads more detail in your features. I would really encourage people to go through and look at them. You can find links in the show notes to both of those.
That was Noah Baker chatting with Heidi Ledford and Kerry Smith. There's a link in the show notes to both Kerry and Heidi's features, which have tons more detail in them than we could squeeze in here, so do take a look.
Coming up, how a chance discovery led researchers to catch a star in the act of eating a planet. Right now, it's time for the research highlights with Dan Fox.
Researchers may have found a new source of cannabinoids, the compounds found in cannabis, in an easier to reach place. Cannabinoids are a group of molecules that have a range of uses, like pain relief and reducing nausea, amongst other things. And so, researchers have been trying to find more sources of the molecules. Now, cannabinoids have been found in the leaves of an unassuming yellow-flowered herb, including a precursor to THC, one of the major psychoactive components in cannabis. And, as the cannabinoid molecules are in the leaves, they are more accessible for any would-be harvesters. The researchers also uncovered the pathways that the plant uses to produce the molecules, which could help scientists trying to grow cannabinoids in the lab. The team hope that this untapped source could help scientists get access to and better understand these powerful molecules. Grow your understanding of that research in Nature Plants. Schrödinger's famous cat thought experiment has been confirmed with a real-life test. Put a cat in a box with a flask of poison which will be released if a radioactive atom decays. What do you have? A source of a lot of physics jokes, and, according to one interpretation, a cat that is both dead and alive, a superposition of states. A useful thought experiment to explain the odd behaviour of quantum mechanics. But now researchers have emulated this idea using a vibrating crystal. By coupling the crystal with a superconducting circuit, the team were able to place the circuit in a quantum superposition. This generated two simultaneous vibrations in the crystal, one shifted in time and amplitude from the other, mimicking the two states of the cat in the box in real life. Other than moving the thought experiment into reality, this also allowed the researchers to probe the confusing line between quantum and classical physics. Let that cat out of the box, over in science.
Stars have a finite lifespan, but they don't always go out with a bang. When average-sized stars like our Sun burn through the hydrogen fuel in their cores, they start to expand to maybe a few hundred times their original size, before they ultimately cool and start to contract. This fate isn't due to happen to our Sun for a few billion years, but it has happened and is happening to countless other Sun-like stars across the universe. And, as you might imagine, this expansion is bad for anything standing in the way. There's a long-standing theory that dying stars consume the planets orbiting them as they swell up in size. But while theorised, this has never been seen directly. This week, though, a chance observation allowed a team to catch a star in the act of snacking on a planet, in our very own Milky Way. Reporter Benjamin Thompson called up lead author of the paper, Kishley Day, from the Massachusetts Institute of Technology to find out more, and Kishley explained what was previously known about these stars as they expand.
So what we've seen in the past is that you see stars that have planets very close in orbits. So you say that, okay, so if a star like this expands, it must engulf the planet that's around it. We also see the aftermath of it, which is that you see these puffed up stars that look somewhat weird in that they have these weird chemical compositions that we don't quite understand because they seem like they've been polluted with material that shouldn't really be in the star. And the natural explanation for that is that it actually got polluted because there was this planet that crashed into it. So we see the before and the after. What we've never seen in the past is catching a star in action like that.
And this is very much where your new paper comes in then. So you might have caught a glimpse of this actually happening. What did you first see that led you down this path to conclude that this was a star essentially eating a planet?
If you want the honest story behind it, I wasn't actually looking for these things. Broadly, I look for things that go boom in the sky, in the sense that if you look at the sky, every now and then there'll be a star that erupts that becomes a lot brighter than what it usually is. And the kinds of eruptions that I was specifically looking for at that time are a type of eruption that we call novae. So what you need to do to find these things is that you ask which star in the sky actually is brighter today than what it was last night. And it just happened to be the case that one night I noticed this one particular star somewhere between 12 to 15,000 light years away from Earth in one of the densest regions in the Milky Way that we can see in the sky. And this star seemed to have brightened about at least a factor of 100 over the course of 10 days. And I thought it was maybe a nova. Except when you find something like this, you want to understand what its chemical composition is. And the way to do that is that you take a spectrum of the source. And novae tend to have certain chemical compositions. They have certain kinds of temperatures that we can infer from the spectrum. But the spectrum didn't look anything like a nova at all.
So you had this spectrum then, which told you a little bit about the composition of the star, but you also saw a lot of infrared radiation as well. What did that tell you about it?
The spectrum that we got looked like it was just surrounded by cold gas. And whenever you see cold gas in the universe, it usually means that there must be cold material around it, which shines very brightly in the infrared bands. So we went and got infrared observations of the source after the outburst happened. And as you were expecting, this source turned out to be very bright in the infrared. And when you see a bright infrared source after the eruption, you immediately question yourself, did it actually do something before the eruption? And that's where we went back and looked at this data from the WISE telescope from NASA that had images of the same part of the sky for the last decade. And what turned out to be the case was that even before the star brightened in the optical bands, this source had started brightening in the infrared bands a year before the eruption. And then it kept shining in the infrared bands even after the star brightened and faded away in the optical.
And astronomers like yourself often see outbursts of radiation from different parts of the spectrum in space caused by different things happening, right? Maybe two things colliding or something exploding or what have you. And each of these has its characteristic radiation output. So here you are, then you got this pattern and you wanted to work out which was the closest match. And it turns out to be these events called red novae.
Right. So what we understand today is that these red novae arise from mergers of normal stars. So if you take a star like the sun and you put another star like the sun very close to it, for most of their life, they're orbiting around each other. Now imagine one now starts to expand as it nears the end of its life. It's going to engulf the star that's next to it. So when you take the characteristics we were seeing in the spectrum together with this huge infrared source that we were seeing, this kind of looks exactly like what we see in these stellar merger phenomena. Except when two stars merge into each other, there's a huge amount of energy involved. These things are so bright, but this star, it was not spectacular at all. This was just a faint example of what we see in red novae. And a natural way to explain that is that, hey, maybe what the star was running into was not another star, but actually something much smaller. And if you just run the numbers, you do the scaling relations for how bright this source is, it turns out that we can actually explain how bright this source is if you just take a normal star and make it 1,000 times less massive. And then you ask yourself, what is 1,000 times less massive than a star? It's basically Jupiter.
And what you're saying is then that this star, as it expanded, it engulfed this Jupiter-like planet. Could you maybe run through the timeline of what's happened to this planet, do you think, based on what you've seen?
So if you put all of this together, right, you were seeing infrared emission even a year before the source actually brightened. So what you have there is that you have a sun-like star that's just beginning to die. It's starting to expand. You have a planet that looks like Jupiter, very close to it. We're talking about an orbital period that's like a day or so. And what is happening is that as the star is expanding, the planet initially just starts to graze the surface of the star. And as it's grazing the surface of the star, it's using its own gravity and pulling out material and throwing out gas from the surface of the star. And that's what we are seeing in the infrared emission, even before the star actually brightens. Now, the sun-like star is like 1,000 times more massive. There's no way this guy can put up a fight. And then in the final stages of the outburst is when the plunge happens very quickly over the course of a day or a few days. And in that process, there is this huge amount of energy that is injected into the star itself. And the only thing that the star can do at that time is expand and produce this brightening that we see in the optical emission. It's just trying to readjust after this huge amount of energy that's been injected into its core.
So it seems then like quite a slow feast to begin with then, before the planet is finished off in a single bite. What's the long-term tail after that? What do you see happening?
So a small fraction of the very outer layers of the star, they expand so much that they're essentially unbound from the star now. But the star actually just goes back to what it was. And that traveling material, as it goes further away from the star, it starts becoming colder. And that's the cold gas that we see in the spectrum. And as it goes even further out, it cools enough that it starts to form dust. And that's what we see in the infrared light. The infrared signature is so spectacular that even today, 3 years after the outburst, NASA space telescopes are still detecting the infrared emission from the source. The dust is still sort of hanging around. So now we can ask, what is the composition of this dust? Does this composition tell us about what the outer layers of the star look like and what the composition of the planet was?
And there's been lots of theorizing about what might happen when a star engulfs a planet. And you've put forward your evidence of seeing one happening in real time for the first time. I mean, what are the chances that this could be something else? Could it have been a merger of two other things, for example?
Obviously, with any scientific work, there's always uncertainties. For us, because this is the first time we are seeing something like this, definitely uncertainties. Like, we think the planet that was engulfed looks like a Jupiter, but it could be anywhere between 10 times the mass of Jupiter, or maybe something that looks like Neptune. But regardless of what it is, the only way to explain how bright it is there must be something that's at least in the ballpark of 1,000th of a star. It really can't be a normal star. It's extremely difficult to explain the properties in that scenario.
And obviously your evidence is out there now. What sort of questions do you think this will help researchers answer?
Because we see only the before and the after, we don't see them happen in real time. There's a huge amount of physical uncertainty about how this process takes place. What happens in planetary engulfment? We think that pretty much every star like the sun has planets around it. So this is something that affects every single star that looks like the sun. So if you find an event like this, you can actually go back and ask the subtle questions that have been impossible to do in the past, which is, how does the star get affected? What does it look like after the planet has been engulfed? In fact, as we speak, our team is getting more data to try to understand what does the star look like right now if we understand what stars look like after they have engulfed planets, we can actually use that to go and ask which of the other stars that we see may have engulfed planets, because we know one now that actually has engulfed a planet.
And of course, here we are on Earth then, and we know that the sun will ultimately expand and consume the planet. Not anytime soon, it has to be said. But does your discovery ever make you think about the ultimate demise of our planet at all, do you think?
Yeah, I think, when we made the first connections, you sort of take a step back and ask, let's say in 5 billion years from now, if I was on a planet that was 10,000 light years away and I was looking at the sun, it would look exactly like this. The sun engulfing first Mercury, then Venus, and then Earth. It would actually brighten, but not as much because these inner planets are not as massive as Jupiter. But you'd see the exact same physics play out. So I think this really drives home the fact that, all of civilization on Earth will essentially disappear over the course of a week or so. And that makes you very humble, in my opinion. You realize how minuscule we are in the scheme of things.
That was Kishore Day from MIT in the US. To read his paper, look out for a link in the show notes.
Finally on the show, it's time for the briefing chat, where we discuss a few of the articles that have been highlighted in the Nature Briefing. So, Nick, what are we chatting about this week?
Well, I don't know if you remember, I imagine you actually do because you were there at the time at the press briefing, the image in 2019 of the black hole at the centre of M87, this first image of a black hole.
Yeah, that was very exciting. Also, didn't really know what to expect when people said image of a black hole, because you're like, aren't they quite dark and absorbing a lot of light? But yes, a sort of beautiful glowing ring.
Yeah, exactly. So this was a story that I was reading in Nature about 2 papers about data sort of coming in about M87 star, the black hole at the centre of M87. So this glowing ring has been reanalyzed to help us better understand what's going on. So in one of these papers, the ring has got a much sharper image.
And just remind me, so what is this ring actually representing? Where is this light coming from?
Yeah, so as you mentioned, you can't actually image a black hole directly. They are so dense that even light cannot escape from their pull. So you can't actually look at them. So what you can look at instead is the stuff around them. And so what this ring was, is it was the light that was being bent around the black hole. So the black hole is so dense, it's bending time and space, and so things get bent around it. And that's what we're seeing. And the glow part, the sort of orangey glow, physicists have thought is some sort of superheated matter that is in the vicinity of the ring.
So this original image was a few years ago from Event Horizon Telescope data. Where is this new image and this new data come from?
So this new image is coming from a reanalysis of that original data from the Event Horizon Telescope. So the way the Event Horizon Telescope worked is it was actually a network of different observatories across the planet that sort of came together to make this image. But because of that, you are kind of piecing together the image from the data that sort of makes sense. And researchers use machine learning algorithms to do this, to combine this data. And so this new image is come from a reanalysis of this data with a different machine learning algorithm. So the original image was done using very conservative algorithms, whereas this one is one that is trying to just maximize the resolution so we can get a clearer, less blurry image.
It's sort of interesting in a way that neither of these images are direct representations of the data in the way that we think of when we think of like photographs of something. They're all sort of certain interpretations of the data. So what does this new interpretation and this new visualization mean? What's the benefit of being able to see it at higher resolution?
Yeah, so this image allows us to better understand like the physical characteristics of the black hole. But I also wanted to talk about, there is another set of data which has been looking at that glow that I mentioned. So this glow, which physicists reckon has come from superheated matter around the black hole, but we didn't really know much else about it. But now they've been able to associate it with a jet that is coming off the black hole. So there's this really ridiculously bright jet of matter that is shooting out of the galaxy, and it looks like it is coming from the direction of the black hole.
So M87 is still very popular in terms of analysing the old data, new data. Is there still lots more to learn about this particular black hole?
Yeah, it certainly seems that there's a lot more that we are learning and we're going to learn about this particular black hole. And now these techniques have been developed for this particular black hole, M87 star. They could be used for Sagittarius A star, which is the black hole at the centre of our galaxy, and could help us better understand how our galaxy formed, how this black hole formed, and lots more interesting things about black holes, because there's a lot of mysteries still to be uncovered. For example, now we've seen that this jet is coming from the vicinity of the black hole, we still don't actually know what's causing the jet, so there's a lot more to actually find out.
Well, if you'll allow me a little segue, how about from the darkest depths of a black hole to the dark depths of the ocean for my story?
I like it.
Which is, leaving space aside, I have been reading, this is such an interesting bit of research, reading about it in the New York Times. It's a science paper, and it's about elephant seals and how they dive down into the dark ocean and take little power naps while they're down there.
Okay, so are they like getting to the bottom of the ocean, sort of laying down, having a little nap at the bottom? It doesn't seem particularly safe.
No, well, so the thing is that these elephant seals spend 7 months a year. This is some research being done on elephant seals in California. These are these massive, great seals, but they have to eat a huge amount. So they spend 7 months of the year just eating fish and squid and things like that out at sea.
Not a bad life.
Yeah. And when they're doing these short power naps, during this time, they're only sleeping 2 hours a day. And, when they're back on land for the other months of the year, they actually spend a huge amount of time sleeping. They love sleeping, possibly because they're not eating at that point. They're sleeping over 10 hours a day. But on land, they don't really have any predators. Whereas in the sea, you've got killer whales, you've got sharks. It's a little bit of a dangerous time. And especially these predators hang out near the surface. So the surface is the danger zone. So your idea about just sort of drifting to the bottom is not so bad. But what they actually do is they do this great big dive, and as they're going down deeper and deeper, they sort of start moving through different stages of sleep. And at one point, this research has found, and this tends to be once you get down to the level at which it would be pitch dark for us, basically, they go into actual REM sleep and have the same sort of kind of like sleep paralysis that we have, where they're sort of completely out of it, basically. It would be really dangerous if a shark came along at that point. So that's why they have to do it so low down. And the researchers have found that they sort of drift, and sometimes they kind of flip upside down, so their kind of belly is up, and they're just kind of spiraling down like a sort of falling leaf. And it's only for maybe 10 minutes they have these quick power naps, and then they just sort of wake up and swim back up to the surface again and then carry on with all their feeding.
It doesn't sound like it would be safer, but I guess, like you said, the predators are near the surface, so it makes sense to go down lower. But how are the researchers figuring this out? I find it hard to believe that elephant seals keep like a dream diary or something, so how do they know?
Dream journal of the deep ocean REM. So, different marine mammals in particular, because they have to come back up to the surface to breathe, sleeping at sea can be quite hard. So, different mammals have different ways of doing it. So some kind of fur seals and dolphins and things do that unihemispheric sleep thing. So, they'll sleep with half their brain at a time. I don't know if you've heard that, and like have one eye open. So, if a predator comes along, they can be awake really quickly and run away. But this researcher wanted to know, okay, how do the elephant seals manage it? So she invented a kind of device like a sort of electroencephalography device. So it can read brainwaves, heart rates, as well as logging where the seal is, so kind of the depth and how they're moving. And it kind of looks like a little swim cap. They just sort of like stick it on top of the seal's head that they were monitoring. And it's recording all that data. So they've got sort of diagrams almost of where these seals are going, this sort of spinning behaviour as they get to the bottom, and their sort of brainwaves and sort of where in the sleep cycle they are at each point.
I mean, does it tell us anything more about how they've adapted to their sort of diving lifestyle, or does it tell us anything more about how we sleep or anything like that?
Well, it's definitely an extreme example of sort of having different types of sleep for different situations. So the researcher was quoted as saying they exhibit unparalleled flexibility in their sleep duration. And she said no other mammal goes from sleeping about 2 hours a day for over 200 days to sleeping 10.8 hours a day. And she also says that she hopes it would actually potentially aid in protecting elephant seals and other marine mammals, understanding their sleep, understanding where they're sleeping, when and where they're sleeping, and help scientists sort of improve the management of their habitats.
Well, I wish that someone would protect my sleeping habitat, because to be honest, sleeping more than 10 hours a day sounds pretty sweet to me. But I think that's all we've got time for today on The Briefing. Thanks, Shamini. And listeners, for more on these stories and for where you can sign up to the Nature Briefing to get more like them, check out the show notes for some links.
And just before we go, a bit of good news. Our podcast has won not one, not two, but 3 awards in this year's Webbies. So we had 1 award for our show How the Black Death Got Its Start, and 2 for our Racism in Health special episode, which includes the People's Voice Awards. So basically, thank you to everyone who actually took the time to vote for us.
Yeah, I worked really hard on that one, so I'm really thrilled that people voted for us. So thank you all for doing so. But that's it for today. Don't forget you can keep up with us on Twitter. We're at Nature Podcast. Or you can send an email to podcast@nature.com. I'm Nick Petrichow.
And I'm Shamini Bundell. Thanks for listening.